Hi, I'm Lavanya. I'm going to talk about building compilers for reconfigurable switches. This is joint work with Lisa Yan and Nick McKeon at Stanford and George Verghese at MSR. Network switches today are fixed function. This talk is about how they're becoming programmable and how to program them. So in the next 20 minutes, I want to get across the following. Fixed function switch chips are very limited, and they'll soon be replaced by reconfigurable switch chips in the next few years. We'll need packet processing languages like P4 to program these reconfigurable switch chips. And thus, we need a compiler to take these P4 programs and compile them to reconfigurable switch chips. So let me show you why fixed function switch chips are limited. This is a model of a fixed function switch chip. As you can see, there are 4 stages. Each stage is dedicated to a fixed function. So in this example, there is an L2 stage followed by V4 and V6 forwarding stages, followed by an ACL stage. Also, these stages are pipelined. That means at any point of time, each stage is processing a different packet. And it only has a few cycles to process the packet before the next one comes in. So we can abstract each of these stages as a match action table that has a fixed match on a fixed header, and it has a fixed set of actions. And if we look at this pipeline and the packet is going through it long enough, you can extract a control flow graph, which describes the sequence of tables that any packet would go through in this pipeline. For example, a V4 packet would go through the L2, V4, and ACL processing stages. So this fixed function chip is supposed to route V4 and V6 packets and filter them based on ACLs. That looks fine. But actually, this chip is too hard for me to use in practice. I can't just add new forwarding or monitoring functionality after I bought the switch chip. The fixed pipeline fixes the control flow for the lifetime of the switch. Here's an example of what I mean. Say I want to add a new encapsulation protocol. There's no stage that can do that in this chip. Similarly, if I want to add a new monitoring action, I can't just change any of the fixed stages and add that monitoring action. And so you see why it took VXLAN 4 years to go from standardization to actually being used in switch chips. And there's a third reason why these chips are limited. I can't even move resources between existing functions. And that could come up a lot. So say I had a huge IPv4 table with lots of forwarding entries, and I had a V6 table that was relatively unused. I can't just move the V4 prefixes to the V6 stage, because that stage can only do a fixed match. It can only look up V6 headers. And plus, I end up wasting all that memory in the V6 stage. Why is this so hard? Well, in a fixed function switch chip, each stage is dedicated to a fixed function. It can only do a fixed match and a fixed action. However, if I can separate the function from the stage and let each stage implement any match action table, then I can do the 3 things I described and more. What do I mean by each stage can do any match action table? That means I can configure the table to match on any header using any kind of lookup, whether it's exact or prefix match, and it can store any number of match entries. And for the action, I can configure it to modify any header using a set of simpler action primitives that are supported by the underlying hardware. So such a chip, where I can implement any match action table in any stage, is called a reconfigurable switch chip. And let me map this control flow back to the reconfigurable switch chip. There are many ways to do this, depending on which table I map to which stage, but I'll stick with the original fixed function mapping. And now let's see how flexible this is. I want to add my new forwarding function. That's easy. Since it has to come before the forwarding tables, I make room for it by moving part of the V4 table to stage 3. Adding monitoring functions is easy, too. I can add a monitoring action to any of these tables. And finally, if I want to move resources between functions, that's easy. If V6 was using any fewer entries, I could simply reclaim that space for V4. So how does the reconfigurable switch chip how does it manage to be so flexible? Well, that's because when I separate the function from the stage, I'm left with match memories and action ALUs in each stage. These are general purpose, which means I can configure the match memory to match on any header, and I can configure the action ALU to process any header. And because these stages are made up of such general purpose unit, they're not pre-programmed to process any particular protocol header. And so I call that stage protocol independent. A switch that is made up of such stages is a protocol independent switch. And now you can see what happened when two tables were in the same stage in this switch. They just shared the resources between them. So one way to look at a fixed function chip is as a match action processor, with pipeline stages and multiple match actions in each stage, in parallel. A reconfigurable switch chip takes this one step further. The match and action in each stage is configurable, and so is the amount of parallelism. Now let me convince you why reconfigurability will be the norm in the next few years. Today's fixed switch chips have 4 parts, as you can see in the picture. They're dominated by switch I/O and memory, and they have wires and logic. Reconfigurability adds mostly to the logic. And in each successive generation of switch chips, the logic is getting relatively smaller as a fraction of the total chip area, which means that the cost of reconfigurability is going down, and it will eventually become negligible. Now let me tell you why logic is getting smaller. It happens so that so logic is getting smaller as a fraction of the total chip area. So why is this? It happens so that in each generation, the switch I/O is about 40%. And they seem to size the match tables larger and larger so that the memory is always the fixed 40% of the chip. And it so happens that the wires are no longer getting smaller at the same rate as logic, which means that logic ends up taking a smaller and smaller fraction of the chip. And so reconfigurability is becoming inevitable. In fact, this is already happening. The fastest switch chips today both run at 3.2 terabits per second. They were announced in the last 3 months. One is fixed function, the Broadcom Tomahawk, and the other one is reconfigurable, the Cavium X-Client. So we believe reconfigurable chips are inevitable. And now we got to figure out how to configure them. So there are a few packet processing languages out there, like P4. So what we need is a compiler that takes a P4 program and compiles it to our compiler target, a reconfigurable switch chip. You already learned a bit about the switch chip. Let me tell you more about the packet processing languages. So I'm going to talk about one such language called P4. What does P4 have to define to use this switch pipeline? Well, first, it has to describe how the parser would extract headers from different kinds of packets. Then it has to describe the match action tables, what they match on, what set of actions they have, and their sizes. And then it has to describe the control flow graph, or the sequence of match action tables that any packet would go through in this pipeline. So what does the compiler have to do now? Well, first, it has to configure the parser. There's good prior work done on configuring the parser. And the second part is that it has to map the match action tables from the control flow graph to the pipeline. This has never been explored before, and this is the focus of this talk. This is interesting because not only does the compiler have to find a mapping that works, but it also gets to explore a lot of benefits of reconfigurability. So what does reconfigurability buy us? Well, first, it lets us use resources efficiently, whether that is by having multiple tables per stage, such as in stage 4 in this picture, or whether it is by spreading a big table over multiple stages, such as the green IPv4 table that's spread over stage 2 and 3. We can make sure that we don't have to leave resources unused. And this means we can use fewer stages. And that, in turn, could help with reducing the pipeline latency or the total power usage. So how do we map the control flow graph to this chip to make the most of this reconfigurability? Our default approach so far, where we map tables one by one to a new stage in the control flow order, is OK. That works because we can make sure that the packet undergoes transformations in the same order as was specified by the programmer. But actually, just like in traditional compiler analysis, we could reorder these tables in order to yield the same outcome for a packet while potentially using fewer stages. How do we do that? We use something called a table dependency graph. So here you see the control flow graph. We can extract a table dependency graph from that. And this graph captures the minimum set of dependencies between match action tables that constrain them to be in some particular order or to be in different stages. For example, here you can see that this graph shows two dependencies between the L2 and the forwarding tables. That's because the L2 table must learn the source MAC address to ingress port mapping before the MAC addresses are modified by the forwarding tables. So that means the forwarding tables can't start before the L2 table ends. There are many other such dependencies. You can look at our paper for more details. And you can also note here that the ACL table doesn't have any dependencies on any of the other tables. That's because I can make a decision to forward or drop the packet independent of what the other tables are modifying. So how do we use a table dependency graph to find an efficient mapping? Here you can see the control flow graph on top and our original mapping on the bottom. Now you can see the table dependency graph. It's very different from the control flow graph. For one, as we noted before, ACL doesn't depend on any of the other tables. And that means we could actually place it anywhere in the pipeline. In particular, we could move ACL from stage 4 to stage 1, where there's room, and end up using fewer stages. In fact, if the switch allows it, we can turn off stage 4 and use less power and reduce the latency. So the table dependency graph helps capture constraints from the program, or dependencies between match action tables. Or to put it in a nicer way, it highlights all the inherent parallelism in the program that we can exploit using this chip. However, we also have to worry about resource constraints in the switch. For example, memory is one big resource. If we don't have enough match memories, we can't move this big ACL table to stage 1. But that's not the only resource we need for match action tables. We need a number of additional resources to make match action actually work. For example, we need resources to carry header fields to the match memories. We need resources to carry data to the action ALUs. And each such resource adds a new constraint to our problem. So we end up with numerous resource constraints. And so the compiler problem is to map the match action tables in the table dependency graph to a switch pipeline while respecting dependency constraints and numerous resource constraints. So to be concrete, we start from a P4 program, and we can get the control flow graph from that, and we can extract the table dependency graph from that. A compiler starts with this table dependency graph and maps it to resources in the pipeline. Is that it? Well, we want to find techniques that are general enough across different reconfigurable switch chips. So we studied two different reconfigurable switch chip instances, the RMT that was described in SIGCOMM 2013, and FlexPipe from Intel. You can see that these two chips are very different. The RMT has 32 stages and abundant resources, while FlexPipe is more limited and has 5 stages. RMT has 2 kinds of match memories in each stage. Most of them support exact match only, and some support ternary or longish prefix match. FlexPipe, on the other hand, has different kinds of memory in every stage. Moreover, these two chips offer different ways for tables to make more efficient use of the match memory units. For example, RMT allows me to combine multiple match entries in the same row of a match memory unit, in effect changing the aspect ratio of a table in this match memory. On the other hand, FlexPipe allows me to interleave match entries from different tables in the same memory unit. So then our revised compiler problem is to map the match action tables in the table dependency graph to the switch pipeline while respecting dependency and resource constraints, and making the most use of features like table shaping and table sharing. So how do we handle all this? Well, our first approach was a greedy heuristic. We prioritize one constraint and sort the tables according to that constraint, and then map them one table at a time to the earliest stage in the pipeline. So here's an example of a table dependency graph and a heuristic that sorts by the number of dependencies that follow a table. So in this case, the heuristic would pick the red table before the blue table, because that has 2 dependencies following it. And then we map them one by one and end up with this following mapping. Different heuristics can yield different table orders depending on which constraint they prioritize. For example, if I looked at this heuristic that's sorted by resource usage, here I characterize that by match width, then we would have started instead with the wide blue ACL table, which needs more resources. And then we would end up with a totally different mapping. It turns out that mapping doesn't fit. However, when there are too many constraints, it's not clear if even one heuristic can find a fitting that works. So too many constraints can be too much for greedy heuristics. Any greedy heuristic must sort tables based on a metric that is a fixed function of the constraints. As the number of constraints gets larger, it gets harder for a fixed function to represent the interplay between all the constraints. And so we need to look for better solutions. Can we do better than greedy? That brings us to the second approach. We use integer linear programming, or ILP. We can use ILP to find an optimal mapping by encoding the compiler problem as an optimization problem. The good thing about using ILP is that we can encode all the constraints in the problem. And we can even optimize for different kinds of objectives, not just the number of stages used, simply by adding a few lines to the program. And finally, we can just plug in our program to existing commercial solvers, and it turns out an optimal solution. However, there are drawbacks. ILP is a black box solver, which means the solutions aren't as intuitive to understand as one you'd get from a greedy heuristic. And second, encoding a problem efficiently using ILP is an art. It took us a few iterations to get to the efficient ILPs we have for the 2 chips. And finally, ILP can be much slower compared to greedy. So here's a simplified ILP setup for our problem. It's an optimization problem, as you see. Here we're minimizing the number of stages. We could use any other objective here, subject to 3 constraints. First, we want to make sure that for every match action table, we assign enough room for all the match entries. Second, we want to make sure that in each stage, we don't use more match memories than are available. And third, we have the dependency constraints. If table B depends on table A, we want to make sure it starts after table A ends. So to understand how our greedy and ILP approaches compare, we ran some experiments using a benchmark of 4 data center use cases from the industry. These use cases differ in the tables, the table sizes, and dependencies between tables. So just to give you an idea of our use case, here's a typical table dependency graph for one of the use cases, and its mapping to the RMT switch chip pipeline. So we compared our approaches on 3 metrics. First, whether the approach could actually fit the program in the chip. Second, how well the approach did in terms of pipeline latency, or the number of stages used, or the total power used for that configuration. And finally, we compared the runtime, or the time it takes to compile to the chip. So comparing whether the approach can actually fit it's more of an issue for FlexPipe, which has a limited number of stages and limited resources. So we focused on FlexPipe. We tried 20 different realistic variants of our use cases and compared what fraction of the programs could be fit to the 5-stage pipeline by greedy or ILP. For comparing optimality, we focused on RMT, where fitting is not a problem because it has 32 stages. So we can actually think about comparing the 2 approaches in terms of different objectives, like pipeline latency, power usage, or number of stages. And for the runtime, we looked at results for both switch chips. So what did we find? Can greedy fit my program? Well, if resources are aplenty, like in RMT, yeah, sure. But when resources are constrained, like in FlexPipe, Greedy has a hard time. We found that for variants of one of our use cases, Greedy couldn't fit 25% of the programs. OK, so how close to optimal is Greedy for the programs that it can fit? We found that it can take 30% more time for a packet to get through an RMT pipeline that's configured by Greedy. So it looks like I need ILP. How slow is ILP? It can be 100 times slower than Greedy, which means it could go from minutes to hours. But that's reasonable if we don't expect these programs to change too often. So if we have time, we should definitely run ILP. But sometimes we may not have time, and then we have to use Greedy. In that case, we can use ILP to suggest the best Greedy heuristic for a program type. So the way we do that is we use ILP to identify critical constraints, or constraints that affect the solution quality a lot for this program type. So we looked at one of our use cases, and we found that the dependency constraint is very critical for that use case, which means if we remove that constraint from the integer linear program, from the ILP, then we can reduce the number of stages for the best solution. This suggests that a Greedy heuristic that targets this dependency constraint would tend to do well. On the other hand, we found that the additional resource constraints were less important for this use case. Similarly, ILP can help identify critical resources. For example, we found that TCAM memories are critical for our use case. If we double the amount of TCAM memories, the best solution takes much fewer stages, which suggests that heuristics that take into consideration limited memories would do well for this kind of program. So in conclusion, parallelism and constraints in reconfigurable chips makes compiling difficult. A table dependency graph highlights all the inherent parallelism in a program that we can exploit. Integer linear programming is a better approach if we have enough time, or when fitting is critical, or when the objectives are complicated. And integer linear programming can help us choose the best Greedy heuristic via the notion of critical constraints and critical resources. Thank you.
Hey, Jun Kim from Jurtech. So great talk. I think this is a really good way to go for the future. My question is, is your formulation of ILP all things like you said you use a data center? Do you know, does the ILP formulation and the time it takes to do that, is it dependent on the topology, the size of the topology?
So the ILP formulation for the switch chip depends on the resources in the chip and how you're going to process the packets.
Okay.
So it doesn't depend on the topology. Your packet program might depend on the topology, but the ILP just depends on the switch chip and the program.
I have another question is did you consider simplifying your ILP so that you kind of sacrifice the optimal solution, but still it's going to have faster time?
Right, yeah. So the solver that we were using, it lets us kind of trade off optimality for time, because you can actually say, I want to be within 50% of optimal, and it would give you a solution faster. But I'm sure there are ways to simplify the ILP formulation itself to get that. We haven't explored that a lot, but yeah, we could look into that.
Cool. Thank you.
Hello, Luis Pedrosa, University of Southern California. So this is fascinating work, and thank you so much for presenting it.
Thank you.
But I'm wondering what kind of tools or optimizations are available in your compiler and that you can then ultimately put as a part into the ILP so that the ILP can explore them as alternatives to try to reduce automatically the size of what you're ultimately putting on the switch. For example, you might have a complex mixture of matches which can be ultimately simplified because the outcome of two completely independent things you never thought of actually is the same, and so you can reduce this. The best analogy I can come up with would be, I think, Karnaugh optimizations in circuits, where if two inputs are different but the outcome is the same, you can just ignore that input, for example. Is there some kind of tool that you can use to do this in here and simplify the program, perhaps optimize the switch?
Right, I think that's a really interesting idea. So you could do more optimization before you actually get to the table dependent. Like, after you get a table dependency graph, you could do more optimizations in order to simplify it further. And then this part is just mapping the match action tables in a table dependency graph to the switch. But if you can do more optimizations before that, that makes it even smaller. Yeah.
All right. Well, thank you very much.
Thank you.
Last question.
Santosh Prabhu from UIUC. I was just wondering if you guys encountered cases where you had loops in the table dependency graph. For instance, due to encapsulation, you feed the packet back into the same switch, that sort of thing. Do you have cases where you have loops and then you have to decide how to lay the tables out? Have you encountered such cases?
Sorry, could you repeat your question?
So my understanding was that the table dependency graph is assumed to be acyclic. Is that true?
Yeah, that's true.
So in the case of encapsulation protocols, for instance, you might want to revisit the L3 table, for instance, after doing the encapsulation. So
Right.
I guess you guys have considered such cases where you have loops in the table dependency graph so that you can come up with a layout for such cases?
Yeah. So we haven't looked at programs where the packet would go through the pipeline again. But I need to think about. I think the table dependency graph, it would definitely work, but you might have to modify it some way. Yeah.
Thank you.
Okay, thank you. Let's thank the speaker.